Chapter 15. This is the second time I'm doing it, so I'm kind of. The first video got lost, and that's infuriating. But this is about how do we know the things that we know about stars, and how do we talk about stars? Stars are obviously different. In this picture, there's uh, pull up the laser pointer. There's yellow and blue stars. There's big stars and smaller stars and tiny stars. There's wide classifications of stars. How do we know anything about them? And that's what this video is about. What I'm showing you here is Orion, which you should be able to see if you go out about midnight tonight. I'd say look east to south. Um, and these named stars here are all very different, very distinct stars. How do we know that they're different? Speaking of Betelgeuse, it was in the news last year for dimming unexpectedly. It's a red giant. We expect it relatively soon in astronomical terms to explode. But we had reason to believe it might do it within a year or so, and then it just went back to normal. It's kind of weird. So there's stuff we don't know about stars, obviously, but we're trying to talk about how we know things that we do know. Again, this is Orion. If you go out in the winter and look, so now you can find this winter triangle, Betelgeuse, Sirius, and Procyon, and Rigel is here, and there's a few other stars. We'll talk about other stars too. This is the closest star to Earth, Proxima Centauri, which is one you'll see from southern latitudes better. It's not that bright. It's not that big. It's really more typical of stars. Most stars are small, dim, and red, and hard to see. So how do we measure? How do we measure anything about stars? Well, we can talk about the various things that we might try to see, and effectively, what we're going to try to measure is the mass of stars, the size of stars, the distance from stars to the Earth, the amount of energy they put out, their temperature, their color. These are the things that are things we can measure. And the first, we're going to talk about the energy output, the luminosity, and the brightness. How do they appear? They appear to us based on how much energy they put out and how far away they are. Right? The idea is that luminosity is just the total power that's radiated outwards. Like a 100-watt light bulb puts out, say, 100 watts of light. That's obviously an overestimate, but um, you can rate light bulbs by the power output, but they output them in all directions. The amount of light you see is based on how much light can go through your eye or how much lands on your sensor. And so it's about the density of that light. It's about the amount of it that reaches Earth for stars, and it's about an energy density or a power density. And these things are related, and they're related based on something called the inverse square law, which is as you move, as you double the distance between objects, the area that light passes through goes as the square of that distance, right? Here we have an area marked out, and the same area is marked out in each of these squares, but when you're a distance r away, you capture a certain amount of light, and when you're 2r away, you only get a fourth of it, and when you're 3r away, you only get a ninth of it. And so basically passes through these spheres around a star, and it's all the same no matter how far away the sphere is. But we're only picking up a little bit of it. And that area of the sphere grows as the radius squared. So we get a formula. The brightness goes as the luminosity divided by 4 pi r squared, 4 pi distance squared. So we can reverse that. If we can tell the brightness, which is something we can measure on Earth. We can measure how much light we get from a star. And if we can measure the distance, we can get the luminosity. So how far away are stars? For these stars in Orion, they're about 1,500 light years away. That's kind of hard to do anything with. For nearby stars, we can use parallax as a way we measure to other we talked about this to measure to nearby stars and how we never could measure it very well before, but now we have the means of measuring it. And again, as a review, as the Earth moves in its orbit, the positions of nearby stars change compared to far away stars. And so if we can measure that change, we measure the angle, that's going to tell us something about the distance. This is just doing trigonometry. And we have formulas for that and define new units. We talked about what's called a parsec, which is the distance in which that angle is 1 arcsecond of motion. And that ends up being about 3¼ light years. So we can find distances to nearby stars. We can use that eventually to bootstrap to other stars. But what we find is the most luminous stars are about 1,000,000 times brighter than the sun. The sun is about 10 to the 26 watts, so we're talking 10 to the 32 watts. And notice those numbers don't seem to mean very much. We're going to talk about units of the sun. The least luminous stars are about 10,000 times weaker than the sun. So, a little bit of history. When we tried to classify stars in ancient history, what we did was magnitude. We had 5 bins, 1 to 5. Class 1 stars were the brightest, class 5 were the dimmest that we could see. And so we fit our modern measurements to those classifications. And we have what's called a parent magnitude, which tells us what the star looks like to us, what our observations show us. And then we have what's called absolute magnitude, which is a measure of the luminosity by saying, how bright would we see it if it were exactly 10 light years away? It's a logarithmic scale. The idea is that the dimmest stars are about 100 times dimmer than the brightest stars, roughly. And here's some classifications. Stars sit in this 0, or actually about -2 to 6 range. And in planets, we'll go from about 7 to -4. And in the very faintest stars we see with the telescope are 27 to 30. The brightest star we can see with anything is the sun, which is -26. So that gives you kind of the range of luminosities we can deal with, range of brightnesses. If you want the gory details of converting magnitude to brightness and luminosity, here they are. Mostly, we're just going to stick with brightness and luminosity. So, how do we measure temperature? So what we have here is a bunch of spectrums of different stars that have different temperatures. And we'll use that eventually. But what I want to say is that there are these classifications that will come up. And we'll describe how they come up. But they're based on these spectrum. But every object emits thermal radiation based only on its temperature. And what we talked about in Chapter 5, hotter objects emit more light. They're more luminous. Their luminosity is higher. And they emit higher energy photons, which is shorter wavelength photons. All right, this is the Stefan Boltzmann law on top and Wien's law on the bottom. You'll read that with a W, W-I-E-N. But these two things that we talked about in Chapter 5, we can apply that to what we see. And what this will tell us is higher energy stars will be bluer. The hotter stars will have higher average energy in the photons. They'll be bluer. Whereas the cooler stars will be red. And we'll see just more light from the bluer stars than we will the redder stars, usually. And what we deduce from surveying a bunch of stars, the hottest stars will be about 50,000 Kelvin, and the coolest stars about 3,000 Kelvin. So very bright blue stars are very hot. Red, dim stars are very cool. The sun is kind of in the middle. It's yellow, and it's about 6,000 Kelvin. So the other place we can see the temperature is in the spectrums, and seeing the ionization of particles in the spectrum of the star. And, this is kind of ballparky, but thousands of degrees, we're going to see molecules of gases and whole atoms floating around. Whereas in the 10,000 and 100,000 Kelvin range, we'll see ionized gases. And so the cooler, so the way to think of this is the cooler a gas is, the more capability it has to absorb light. And so the more spectral lines we'll see out of it. The more ionized a star is, the less stuff it can absorb on its own. And so that's what we see in these spectral types. The hottest stars, which have this classification O here, are basically just hydrogen spectra. Whereas the coldest stars, which are classified M, have molecules in them. And so they have more spectral lines. This is a way of categorizing stars, and people did this. They categorized stars by their spectral type. And they developed a spectral type in different groups, and for various reasons that I don't know, they didn't go alphabetically or numerically. They went O, B, A, F, G, K, M, from hottest to coldest. And I should tell you a bit about the development of this. And it comes historically. Here is the way stars might look in these different spectral classes. Though what you're going to see is basically measuring brightnesses and looking at different spectra. And who did that? Well, 100 years ago, there's observations about spectra of stars, and then there's a need to calculate that data. And calculators, today, you know what calculators look like. They're the boxes you take the test to poke your numbers in. 100 years ago, it was a profession, mostly done by women who worked at the universities, and effectively they did astronomy. They looked at the data and categorized it. And so they came up with these spectral type classifications in their calculating the various spectra that they were seeing from data that had been gathered. That's how we get temperature, and that's, talking about spectral types. You don't. I want you to know about spectral types, but it goes into more detail on that, and this is the limit of what I want you to know. Basically, can you reason out that there are spectral types? So how do you measure masses of stars? If we wanted to measure masses of planets, we would use Kepler's third law. If we want to measure exoplanets, we use that in addition to things we can measure. And so we do the same thing with stars. We look for, basically, stars orbiting other stars. And there are enough binary systems that we can do that very well. And it's only going to depend effectively on the strength of gravity between the two stars. So based on the masses of the stars. The way we categorize types of observations of exoplanets, there's types of binary star systems. The ones you can see visually or astrometrically, measuring the wobble of the star as something orbits it. You can do spectroscopic, which is measuring the Doppler shifts. You can do eclipsing, which is measuring essential lights. And about half of all stars are in these systems, so we usually get fairly good data. At least we can measure some stars' masses. All right, so, visual binaries is just measuring the change in position. Spectroscopic binaries is just measuring the Doppler shift between, as one star orbits the other, goes away or towards us. And then eclipsing binaries measure the change in intensity as one star eclipses the other. like this. But once we have of the some measure of these properties, right? Remember, like for Doppler shift, you get the orbital velocity. For the visual, you get the size of the orbit, the average separation, and from all of them, you can probably get the period. Two of three different things: period, radius, or velocity. And then from that, you can get what you need to use Kepler's third law. And so that's how we calculate the masses of systems. And what we get out of that, and I want to say take this with a grain of salt for the most massive stars, because every time we set a limit on the massive star, there's one that breaks it. So think of these as orders of magnitude. For most massive stars, 100 solar masses. A solar mass is 10 to the 30 kilograms, actually 2 times 10 to the 30 kilograms, but imagining 10 to the 30 kilograms is kind of hard. It's like imagining $1 billion. It's pretty hard to imagine, so we'll just take units of the sun. Most stars are about 100 suns, most massive stars. Least massive stars, this is more concrete because it's smaller. They're about 800 suns. All right, so we talked about luminosity, temperature, mass, and from all those measurements of binary stars, we can get size as well. Uh, so, and we can get some other measurements in different ways. But how do we use that to tell us? One way is to to eventually, and to do that, we use a tool called a Hertzsprung, and it lets us plot populations of stars all together and compare sets of stars to each other. And the idea is it's a graph that plots the luminosity and temperature, and we get other stuff out of it as well. So here is another one, and you can see it plotted differently. All right, two axes. We have luminosity on the left, temperature on the bottom. Although actually, this is color. So temperature would really be at the top, spectral class at the top. But the way we do the measurement might be measuring at different wavelengths to measure how much wavelength we're seeing from each one. And then you can also, so we describe it as luminosity and temperature, but it might be something like magnitude, which we can in principle measure, and intensity at different wavelengths. Right. So just be aware of temperature, but in general, that's the information that matters: is luminosity and temperature. And what we see is that there's different classes of different families of stars that have different properties. So the and it tells us some other stuff along with that. But what we see is that there's different populations of stars. Most stars that we see fall along this one line that goes from very cool, small, dim red stars up to larger, more massive blue and bright stars. All somewhere along this line. It's what's called the main sequence. But then some stars will be at a different point in their life cycle, and they will have lower temperature and higher luminosity, which means that they're larger stars. They'll sit amongst the giants and supergiant families here. And then some stars will be higher temperature but lower luminosity, which means they're smaller. They sit in this population, what's called the white dwarfs. And so you can come up with different categorizations of stars, what's called the luminosity classes. I don't expect you to know this. but you can see those. So you can get some information, the temperature, and also color, the spectral type, and then the luminosity, and from that you can get the radius. Part of these slides is, can you read one of these charts? The hottest stars are the ones most to the left on this chart. Notice it runs from 3,000 to 30,000, and it runs right to left. So in this case, the hottest stars would be A. The most luminous would be the highest up on the chart, which is C. The main sequence star is the one along the line, which is D. And then the largest radius is one effectively up in this right top corner, which is C. So, what is the significance of these populations? What is this main sequence? Well, it's fusing hydrogen into helium. That's the typical main chunk of its life. And when a star is on the main sequence, it represents a typical star that is burning hydrogen into helium. And so there's different classifications here. The cooler stars, the yellow and red stars, are going to be less luminous and smaller. And the bluer stars are going to be more luminous and more massive and hotter, which is telling you something about, remember, the energy output, the luminosity, is based on the fusion rate. So these cooler stars are burning fuel more slowly, and the bluer, hotter stars are burning fuel faster. So this is also telling you a little something about its lifetime, which is happily put in the chart in green here. And that's, telling you this other, high mass stars are going to be sitting on this line in the blue positions, and they're going to be much, much bigger than the cooler red stars. And so almost every other feature of the star. But the mass is going to determine the luminosity and the spectral type, the temperature, and it's because the core pressure in a high mass star needs to be large, and high core temperature, high core pressure creates more fusion. It creates, so what we'll note is that these things are all in the same trend. Luminosity and temperature and mass all go the same way, and mass is the thing that determines luminosity and temperature. All right, mass is going to be the most important property that determines everything else because of the way this works, because mass determines the rate of fusion. So we can talk about life expectancy, and we estimated for the sun that its life expectancy is 10 billion years. If you have a star that's 10 solar masses, what we find is it uses that fuel 10,000 times as fast. And so we expect a 10 million year lifetime. For a star that's a tenth the sun's mass, well, it's a tenth as much fuel, but it uses it 100 times slower, which means it'll go 10 times as long in life, 100 billion years. So what we expect is massive stars live less, and smaller, low-mass stars will live longer. So summarize what we see of main sequence stars. The high-mass stars are high luminosity, small, short lifetimes, large radiuses, and they are blue. Low-mass stars are low luminosity, long-lived, small radius, and red. Now, of course, once we get away from main sequence stars, those things kind of go out the window because other processes are going on in the stars. That's why we talk about what giants and dwarfs are. All right. And to compare, what we mean by giants is and dwarfs, So we pointed out the Procyon is a star uh, in that winter triangle, and so is some of the other stars. Uh, some of the other stars will also have this. Is they have companions that are very small, bright, high temperature dwarf stars. They're very small stars that fall in the category of white dwarfs, and they're about a tenth to a hundredth the size of the sun. And then giant stars, and we showed these at the very beginning, identified where they are. Um, Stars that are 10 to 100 times, they're significantly larger than the sun. And what we find is that these larger stars are also cooler. And if we go back, these dwarfs will be, in general, hotter. It seems a little counterintuitive. It's not what the main sequence stars are doing. These stars are doing something different. They're in a different stage in their life. And effectively, the main sequence properties are based on the star fusing hydrogen to helium. Once it stops doing that, then they change their group. Once they exhaust more hydrogen, they grow larger and cool off. They become giants and supergiants. And once fusion has ceased in total, generally the stars end up as the core remnants, which are very hot and very small. They end up as white dwarfs. Later chapters will go through the process of how does this happen. So, again, can you read this chart? Which star is most like the sun? Well, we're looking for a yellow star on the main sequence. That's B. Which stars will change the least? It's got to be the stars that have long lifetimes. Stars are no more than 10 million years old. Looking for something blue. That's A. All right. So we described all these properties and measurements. But what if you go back another day and you measure something different? That's a little weird. And we found stars that do that. There are stars that vary significantly with reasonable amounts of time. They're what we call variable stars. And what's going on? Processes going on in the star. We assume that there's this negative feedback, like the sun has, that keeps things nice and steady. But some stars don't achieve that easily. If you're interested in this, that's something you can go into, like electrical engineering or mechanical engineering, processes, control methods. I think even math classes will have that in some places. But the idea is that some stars get too big, they get too small, and they oscillate. It allows that negative feedback to work steadily. So they alternately expand and contract, and they change, they vary brightness. And you can see a period in it. And so here we plot apparent brightness for a star over time. And this is over days, right? Not over like years or decades or centuries, but over days. What we find is that this particular star has a period that's about 50 days. A lot of these stars set on what's called the instability strip, um, which is just kind of hanging off of the main sequence. And certain categories of stars, the first ones that were discovered and their properties, they're going to be useful to us later. And so we'll bring up that the most luminous ones, the easiest ones to see, are called Cepheid variables because they're named after variable stars that we found in the constellation Cepheus. All right, so here is an example um, of one that we found that has a period of 40 days, and its luminosity is about 15,000 times the sun's luminosity. And the way we measured it is kind of interesting, is that we measured it using light reflected to us, and it let us get really accurate period and luminosity and distance measurements all So the discovery is this is kind of interesting in that calculation work. Calculators for calculating the spectral classes. There were also people who realized that there was a relationship between the period of these variable stars and their luminosity. They did this. Um, and so, in particular, the discoverer is this Henrietta Swan Leavitt, which you should definitely look up about. Found this in a set of measurements of stars. Um, Found this particular period luminosity relationship, which is going to be useful for us. It's going to let us find distances to things because this is a function of the physics of the star, and that's independent of where you are. So we can deduce from the period luminosity, and that lets us deduce distances from luminosity and brightness. All right. So Hertzsprung-Russell charts and such, and different regions in them. How does that let us know about other stars? How do we use these charts? And to talk about that, we want to talk about populations of stars that we can look at. And so the sun is unusual in the sense that it's alone. Is that there's some nearby stars, but in general, it's not a binary star. All right, about half of all stars are, so the sun isn't completely unusual. But there are larger groups of stars that we've shown comparisons here. This one on the left is the Pleiades. I don't remember the one on the right, but these are the types of clusters of stars where there's larger populations we can look at. And right now, at the moment, the differences we can see in this group, the Pleiades on the left, is a few dozen, maybe 100, and they're all blue stars. Or very nearly all. I can see like one or two yellow ones. But the majority of things are very blue stars, which, from our previous knowledge, youthful stars, they don't live that long, massive stars, bright stars. The other population over here, there's tons and tons and tons of them, and they're all yellow and red. Lots of red stars that you can see, you can distinguish. And that's going to tell us old stars, small stars, dim stars, cool stars. So the Pleiades is an example of what's called an open cluster. Up to a few thousand stars. They're not very packed. They're kind of just loosely together, but they're all fairly close to each other. And you can see from these that they're going to be generally younger and bluer stars. The Big Dipper is in a cluster, and you can see lots of those stars. Lots of the. So when you see asterisms in the sky, what you're seeing is generally the projection of the stars on a flat space. They're not always in the same range, but certain constellations, certain asterisms, actually are. They are clusters, and the Big Dipper is one of them. So different clusters. The top one up here is the Pleiades, which is if you go out and you look for Orion, then you're going to look for Taurus, which is to his right, basically a hunter hunting a bull. And on the back of the bull is this small little group of stars, very small little group. You can see 7 of them. They were called the Seven Sisters. But there's more of them that you can't see. And then lower down, the Hyades cluster, we'll point out. Pleiades, Hyades. So those are open clusters. A globular cluster is it's a cluster of 1 million or more stars, and they're held by gravity, and they're in a very dense ball. All right, so here's an example of 10 million stars in a cluster. And in seeing some in infrared and visible light. Now, there are some younger clusters. You can generally, globular clusters seem to form when the galaxy forms. They seem to be very old stars in a galaxy. But there are some younger ones, and we'll show those too. But the point of this is all the stars in a cluster through their life cycle at the same time. The massive ones are aging out first. So if we plot them on one of these HR charts, what we will see is most of the stars sit on the main sequence, like this plot of the Pleiades, but some of them have drifted off. And that sets a limit. That tells us the age of some of these stars, is that these stars that have just turned off, they're going to be about 100 million years old. So that sets a limit for the age of the rest of the stars. It's that they're at least, the life expectancy is at least a certain amount. So the turnoff point, the point where you start seeing stars not on the main sequence, tells you the ages of stars. And it's because the first stars to die are the most massive, bluer stars. And then they're followed up by the less massive and cooler stars. So we can model the evolution of a cluster of stars. And here we've put in 4 different clusters. And, the youngest clusters have very massive stars still on the main sequence. And the oldest clusters are down where we're starting to see yellow stars turn off. All right. The idea is that when we model the oldest clusters we can see, we figure that they're about 13 billion years old. They seem to be about the age of the universe itself. They seem to be some of the first things that have formed. So here is a cluster that seems to be 12 billion years old, we think. Now, the question about this, if you look at this carefully, so this is its HR diagram, and this is plotting color index here, which will effectively be the temperature and the brightness. And we can see that there's a turnoff, but getting from this, we're getting that this is 12 billion years old. But if you look at it, there's blue stars. That doesn't make sense. So we tell you this stuff, but we find some really weird stuff out there. All right, so this is the red giant branches turned off. This is the main sequence that we see. And what we're plotting is color index, which is saying blue stars are high temperature, red stars are low temperature, versus the brightness, which, since all these things are in the same spot, is telling us the luminosity. And so what we see is that there's this turnoff that tells us an age, but it doesn't match what we're seeing. It doesn't match that the stars are blue. So there's interesting stuff going on. And these blue stars that we see in an older cluster are what we call blue stragglers. And it's possible that they weren't created with the cluster, or it's possible that they were created after the cluster out of other materials, or maybe that stars can merge and that changes since effectively you get a more massive star, they suddenly are bluer. So that's stars and clusters. And I want to go all the way back to the beginning. All the way back, all the way back, all the way back. All the way back. This picture. This is a thing about the lifetime of a star. The lowest lifetime we mentioned was something like 10 million years. And the longest one was 10 billion years. Or longer, 100 billion years. we can't observe the life of a star in any way. Our life is just too short. All of recorded history cannot hold the life of a single star. The principle that we have here is we have to deduce the life cycle of a star by looking at the entire population of stars. And we're constantly finding new stars. That's the thing, is that we deduce, like, as students, as young people, you deduce that there are also old people because you know old people been old. That's what's happening here. We see young stars and old stars, and from that we deduce what must be the life cycle. But this is also as if we're meeting new people. We learn new stuff about it. We find new stars that gets us to the end point. We'll talk about clusters and finding unusual clusters that tell us new information. Maybe there's stars that merge and they survive the merger. So we're learning, but we're learning by surveying stars as they appear to us now. So keep that in mind, is that as we do more observation, we learn more, and things may not be as I present to you because I'm doing the best I can with year-old information, and maybe stuff gets discovered. That's why I gave you an assignment, an optional assignment, this research thing, to go and find where I've been wrong. Find a star that is interesting and gives us new information. So that's the video. If you have questions about the homework or the assessment or anything, please email me. I'll try to have another video up later for the next. Otherwise, have a good day.